All right, welcome everybody. My name is Marco Palladino. I'm the CTO and co-founder of Kong. Today we're going to be doing a couple of things. We're going to be exploring service mesh as a pattern to understand what it is and how to implement it. And then we're going to be looking at a more hands-on demo on how to use our service mesh implementation that's called Kuma, why Kuma is different, and how we can use it to implement some very common use cases that Kevin will demonstrate. So Kevin, I'll let you introduce yourself.
Hey folks, Marco, can you hear me all right?
Yeah, we can hear
All
you.
right, perfect. Yeah, my name is Kevin. Nice to meet everyone. I'm the developer advocate at Kong that focuses on our open source technology and enabling the community to use those technologies to be successful in their day-to-day job. And I'm going to be working on, I'm going to be illustrating how to use Kuma in a real-world example via our Kuma demo application after Marco does the introduction. So Marco, I'm going to hand it back to you.
Yeah, so let's start talking about what service mesh is. When talking with users, with customers in the community, I noticed that there is a little bit of confusion as to why service mesh is happening now, what it is, and how we can implement it easily. So I would like to take a step back to understand why the industry created something like service mesh in the first place. A few years ago, the industry entered an important transformative shift. This market transition was triggered by a few technologies like Docker in 2013 and Kubernetes in 2014. Docker and Kubernetes changed the industry in a significant way. The industry itself was going away from those large monolithic code bases that are hard to deploy, they're hard to scale, they're hard to iterate on as the teams get bigger and bigger. And the industry was already transforming towards more decoupled and distributed systems. And some companies like Amazon, like Netflix, they really entered this era of microservices a long time before Docker and Kubernetes were released. But in order for Amazon, Netflix, the Googles of the world to be implementing this transformation, they had to build from scratch all the tooling and all the platforms that would allow them to do that. The important thing about Docker and Kubernetes is that they enable every other team and every other organization to make that microservices transition without having to worry about building from scratch that tooling. So when Docker comes out, with Kubernetes comes out, and when this new ecosystem that's built on top of these technologies really comes out, they really change the way we build software. Like I said, from large code bases to smaller code bases, distributed, decoupled, perhaps by leveraging the cloud, as well as they also trigger a transformation in how we're building teams in order to be able to create this software. And the teams are becoming as distributed and as decoupled as the software we're building. So really what Docker and Kubernetes did, it's not just a technology transition, but it's also operational and organizational. So when we look at this shift, it really revolutionized how we build software and how we drive new business. And it's being led by those important technologies. It's being led by technologies like Docker, like Kubernetes, and also by new patterns and new vendors. For example, clear winners are those cloud vendors. Clear winners is Kubernetes and orchestration platforms, and containerization platforms like Docker. Clear winners are new ways of monitoring our software and collecting those metrics and showing them on a dashboard, as well as collecting traces like Zipkin, like Jaeger. And also clear winners are self-service ecosystems like CNCF, where basically, if you look at the CNCF landscape, half of those logos did not exist half a decade ago. And now they include products and tools that fundamentally allow us to operate in this new world of microservices and distributed software. Effectively, the way we build the software is different, but also the way we deploy it, the way we operate it, the way we monitor it. And so it's a revolution really in how we're building software. And during this transformation, new technology patterns emerge. First of all, we have to take a step back and understand that every time there is a technology transformation, it's always been triggered by a fundamental business goal. And our goal is to create more reliable software. So when we look at the digital world, right, and what we notice are two trends. The first trend is that every company is becoming a software company, and every company is becoming a technology company. And the second trend is, as a result to that, every product is also becoming a digital product. And when these products become digital, then we need to make them reliable, and we need to make them we need to be able to get new customers and make existing customers happy. Therefore, we make them distributed, we make them highly available, we leverage the cloud, we leverage whatever we can in order to achieve those business goals. Effectively, decoupled software is good for business. And in this new era of software, we celebrate the importance of service connectivity as the underlying enabler to this new way of building software. If you think about it, in a distributed and decoupled world, our distributed and decoupled services run on the network. And to connect them together and enable these service-to-service traffic, we leverage APIs. APIs are becoming the underlying backbone of our new systems and our new software. So when we talk about services and APIs, really what we mean are all the types of services and all the types of APIs that are running in our systems. So we're talking not just about traditional HTTP services that historically, we would create HTTP services to connect them externally. So we would create a mobile app, or we would want to create a platform, so a developer community that would come in from outside and consume our software. Well, now APIs and services have a much bigger scope. It's also databases, anything that listens on a network. So a database, a log collector, a caching system, all the microservices that we build and that make our applications usable to the end users, each one of these systems is a service. And in order for these services to communicate together, they need to expose an API. Therefore, APIs are not just HTTP APIs, but they become gRPC APIs, GraphQL APIs, TCP APIs, all sorts of things and technologies that would allow us to connect these systems together. The most radical underlying shift from monolithic applications to microservices is replacing the CPU with the network. In a monolithic application, we make function calls. Everything is being deployed in a large binary, and we make function calls among the different objects that we are exposing within that code base. But in a distributed system, we make API calls on the network to consume all the services that we need to consume, and that over time, they've been decoupled. This is a big shift in the reliability of our apps, because the CPU was reliable. If we did make a function call, that call would be executed by the underlying virtual machine, for example. But when we make an API call, well, because we're going over the network, now we're introducing a big variable into the reliability of our systems. Why? Because the network is unreliable, as we all know. But of course, we always had network traffic even before. So when we think about a monolith consuming a database, well, that request, of course, was going over the network. But what has changed between now and then is the number of services that we have that overall define a bigger number of network requests. The scale of our network requests is much bigger in a decoupled, distributed, microservice-oriented architecture. Like I said, we're transitioning to this because it's easier to decouple the concerns from different teams. It allows the teams to deploy much faster so that we can implement fixes and features much faster. Therefore, we can make the existing customers happy and also be more likely to get new users. At the end of the day, it all reconnects with the broader goal of increasing our business, right? And so we're making these transitions because it's good for business. At the same time, there's pros and cons. And as part of the equation for microservices, one of the big cons is these network requests. We're making many of them, and we have to do something about it. Now, like I said, making network requests, I mean, this is something that we've been doing for a long time, even in a monolith. And, per se, the biggest difference is that, in the monolith, the CPU was reliable. The monolith was hard to scale, was hard to build, was hard to deploy, but at least those CPU calls, they were working well. So if we called a function, that would work. And the monolith, of course, it didn't scale, and we had to replace it, and we had to decouple it. But by doing so, we've also replaced the reliability of the CPU in the monolith with the unreliability of the network, because now lots of those function calls are API calls over the network. And the network is problematic because it does introduce a series of use cases that we need to take care of. And some of them are, for example, encryption. We want to be able to encrypt the traffic between different endpoints in our systems. We want to be able to identify our workloads, and we want to be able to set up ACL rules to determine what service can consume another service. We want to be able to release new versions of our products, new versions of our microservices. Therefore, we need to have more complex routing rules that allow us to do things like, for example, blue-green deployments or canary releases. We are going to be having all of these network requests running along our systems. And then if something goes wrong, well, good luck finding out where it goes wrong, unless we implement solid observability, we implement tracing, we implement logging, so that when something goes wrong, we can exactly pinpoint where it went wrong. And then, of course, we want to build all of this in such a way that in a zero trust environment, so that we know that nobody can impersonate, no service can impersonate another service. We want fundamentally to improve the reliability of our systems. So the security aspect, it's quite interesting because on one end, microservices, they make security problematic because we do have to implement that transport security on the network. On the other end, and this is a feedback that I've received from many users or architects that have transitioned to microservices. On the other end, microservices, they improve security because they allow us to implement more fine-grained security rules that in the monolith were very hard to implement. In a monolith, if you have access to a class, you can then invoke those the functions that are being exposed by that interface, and there's not much fine-grained security being implemented usually. With microservices, because they run over the network, we can use network security to fine-grain a little bit better how we want security to operate across these different services. But so even back then in the monolithic world, we would take care of that connection. We said the connections are problematic because we're going over the network, but the monolith would do something to deal with that. For example, we would either we would write code that reacted to a faulty network connection, that would log that request, that would try to deal somehow with that network connectivity. If the database goes down, usually we would catch that exception in our network connectivity and then implement a failover. But we also know that most of the times, none of this was ever implemented. How many applications do we know that are going to fail with no recovery attempt or no meaningful logs when, for example, the database request fails? We know that this happens all the time. And the network management really becomes a little bit challenging here, because if we do it, then the more monoliths we create and the more fragmentation we have. And if we don't do it, we cause a disservice to the end user. But let's assume that we're not going to ignore the network. Let's assume that indeed we're going to be building some network management in our app to make sure that the connectivity across our services, in this case across the monolith with the database, is always going to be secure, observable, up and running. And this is really when, in a large organization, some problems start to happen. The application teams will build something for their own monolith, And then another team will build another monolith, and they will build their own version of their network management in a slightly different way, or perhaps in a different language, different monoliths, different apps using different programming languages. All of a sudden, we end up in a situation where we have a big fragmentation in the way we manage our traffic. And that is a big problem, because when we fragment how we manage our traffic, we also fragment how we secure those connections. We fragment how we observe those connections. We fragment how we implement routing strategies when it comes to moving traffic over to healthy services, or perhaps reducing the latency and so on. Basically, by letting the teams manage their network, we fragment the entire architecture. And the team's job, it's not managing the network. At the end of the day, our application teams, their goals is to build an app that the end user will use and consume, right? The business logic they have to build, it's the application they're building. It's not managing the network. So they're doing something that they shouldn't be doing here. And this will cause irreparable damage in the long run to the entire organization. And in a way, it also promotes shadow IT practices. Now, as we discussed before, over time, we're going to be decoupling and distributing our software more and more. And this problem all of a sudden becomes so large with so many services that it can really harm our velocity and our direction. So we need to do something about it. At the same time, we really cannot ignore the problem. I guarantee you that every organization in the world has built applications that are reinventing network management. We don't want to let the teams manage with their network the same way we don't want them to manage with their data center, right? We want the application teams to provision software in a specific way, to provision the hardware, the virtual machines, the containers in a specific way. Well, likewise, we don't want them to be managing their network. We, the architects, want to give them a turnkey solution out of the box that will always work. So maybe we can build all this network management in such a way that regardless of what programming language or framework we're going to be using for our apps, for our services, we can always provide those network connectivity functions to all of them by shipping them in a separate binary. If we collect all of these common functionalities for managing the network and we put them in one binary that's separate from our services, it's separate from our monoliths, it's separate from what the teams are doing, well, the binary, now it's portable. We can compile it and then run it pretty much across every service. It doesn't matter how the service itself is being built in the first place. Now, if we want to offload the network management to a binary that takes care of these concerns, for this to work, that binary needs to be on the execution path of every incoming and outgoing request, like a proxy, so that we can enforce security policies, we can enforce TLS termination, we can enforce logging, and so on and so forth. And while it is true that we would have another component on the execution path of our requests, at the same time, having this component in between that allows the teams to not worry about managing their network anymore. The concept would be that the proxy, like a proxy, would then intercept outgoing requests and implement security, routing, observability. On the other end, we would be having another instance of the proxy. Therefore, when the services are consuming each other, in reality, they're never making requests directly to each other, but they're always going through this binary proxy. And this proxy, this binary, would then take over that connection and go on the outer network. This becomes worth it because we have a new element on our execution path that does all of these things. It's really worth it if this entire thing does not add too much latency. At the end of the day, we're going to be having a new hop in the network because we have this proxy. And so if the latency is too high, then this is not gonna work. So with a proxy binary alongside our applications, there we go. Before I actually jump on that, I want to keep focusing on the latency part. I forgot one thing. Because the latency shouldn't be shouldn't be high, and we should always try to reduce it, we're going to be deploying these proxies on the same underlying host, virtual machine, or pod as our services, because the local host latency between the service and the proxy, it's always going to be minimal. So this works, obviously, if the benefits that the proxy provides are higher than the latency, then this is a pattern or a deployment that we can support. And now, let me go back here. So with a proxy now, alongside our applications, we can now add as many services as we want. And if we build them ourselves, because remember, a service can be a database that we download and deploy. It's not necessarily something that we build ourselves, but a service can also be a microservice we're building. So basically, we can use whatever programming language, we can use whatever framework to build our services. And the proxy binary will always work into managing the network connectivity, because the proxy binary being an out of process proxy, a separate process, it's portable by definition. As long as we start this process alongside our services, it's always going to be to work. But most importantly, all the service connectivity policies are now being managed and configured in one place. This also speeds up the application development, since the teams don't have to worry about creating that network management in the first place. This proxy binary does it for them. They only focus on building their apps. When they make an outgoing request, the proxy will take it from there and make that outgoing request. And when a new request comes in, the proxy takes that request, implements the TLS termination, for example, and then reverse proxies that request to the destination service. Basically, the proxy binary does all the complicated networking stuff. The service just makes requests in and out and delivers and delegates the network to the out-of-process proxy. Now, of course, like I said, we always had network traffic even before transitioning to microservices. Like I said, think of a monolith consuming a database. The request goes over the network. And this proxy, obviously, it's going to be working regardless of what architecture we're going to be supporting. So we could have a monolith talking to a database. Sure, the proxy will take over that request and make that request in a secure way and observable way. If we have many microservices, that would still work. By this, I'm trying to say that the proxy does not make any assumption as to what architecture we're using. As long as we're making a request over the network, we could be using this proxy to manage the network for ourselves. Also, it doesn't matter where we deploy our services. We could be deploying them on a virtual machine. We could be deploying them on Kubernetes. It doesn't matter. As long as we make a request outside of our services, then we can take advantage of something like this proxy. Now, because like we said, this is only worth it when the latency between the proxy and the service is minimal, we would also want to run the proxy as close as possible to our services. So in the case of a virtual machine, we would want to run this proxy alongside our service process. And in the case of containers, we would want to run this proxy on the same underlying host where it's being scheduled, on the same underlying host as the service that we want to help with their network management. So for example, in an orchestration platform like Kubernetes, we would deploy this proxy as a sidecar container. Sidecar container is just a fancy word to say that we're going to be asking Kubernetes to deploy the proxy on the same underlying virtual machine where the other service is going to be deployed. So we always want them to be together on the same underlying virtual machine, because like I said, we always want the connectivity between the proxy and our services to be on localhost, so that we can cut down that extra latency since we're making an extra hop in the network. And obviously, in order to support this new way of managing the network, we have to change a little bit our deployment process so that we can start this proxy when we start a new service. So for example, if we were running these on an EC2 virtual machine on Amazon, we would start let's say our service is a Java service, we would start the proxy and the Java service on the same underlying EC2 instance, right? So we need to change how we deploy our software so that the proxy is always going to be there when the service starts. Because if the proxy is not there and the service wants to make a request over the network to another service, well, now, that proxy is not there, it cannot take over that request, therefore it cannot implement all the features on the network, like security, routing, observability, and so on, that we want that proxy to do instead. So there are different ways we can do this, but the industry standard now is to run an instance of the proxy across each replica, across each instance of each service. Let's say that we have a monolith and a database. Let's say that we have 5 replicas each, therefore we have 10 different instances. So we're going to also be having 10 different instances of the proxy running in our systems, one for each replica of each service. Of course, we're going to be having many of these proxies running around, which means the proxy itself must be very lightweight. If it's not lightweight, if it's not small and doesn't consume just a few resources, if it consumes too many resources, then the proxy itself can be problematic because it can consume the underlying virtual machine resources, and we don't want that to happen. Again, we're going to be having one instance of this proxy for each instance of our services. Therefore, in the grand scheme of things, the proxy really has to be fast and lightweight. Since the proxy will be dealing with the inbound and outbound service connectivity, well, there must be a way for us to configure this behavior. We want to configure, how we want to execute the mutual TLS termination. We want to configure the routing rules. We want, to be able to configure the behavior of the network, since now the proxies are taking over that network. Well, the simplest way to do this would be to start the proxy with a configuration file. Like, we start the proxy, we pass a configuration file, and in that configuration file, we determine what the network policies should look like. So how the mutual TLS should look like, how the logging should look like, what's enabled and what's disabled, and how they're configured. But again, this can be very problematic, because if we ever decide to change that configuration, well, now we need to restart the proxies or reload them with this new configuration file every time. And again, we're going to be having many of these proxies around, and there must be a better way to do this. So what if, instead of having a configuration file that we deploy alongside our proxy every time, what if we push that configuration in one place that's external to all the services and all the proxies? What if we put it in some form of database almost, where the configuration goes in there, and then there was a way for us to propagate that configuration from this source of truth to the proxies in a dynamic way. This component we could be calling the control plane, or the configuration service that manages all the configurations to all the proxies. Every time we want to make a change, we would make it once in this configuration service system, and then that system will propagate the configuration to these proxies. Now, if we did that, we have solved a big problem. We don't have to now configure these proxies independently from each other every time. And if we do change something, well, it's all dynamic, right? This configuration service will dynamically propagate the configuration to the underlying proxies. So we can call that the control plane. We call it the control plane because it controls the proxy, and it's not on the execution path of our service-to-service requests. This control plane, what it does is connecting to the proxies, not to the services, but to the proxies, so that we could dynamically configure them if we want to make some behavioral changes in how we want to manage the network. The proxies, on the other end, are going to be on the execution path of every request. They represent our data plane because they process all the data that goes in and out from our services. In short, we can call the proxy the data plane proxy, and the control plane, we can just call it the control plane, right? So we have a data plane proxy that implements all the network functionality that's running on the execution path of our requests. We're going to be having one instance of this proxy binary for each instance of our services on both ends. And then once we want to configure the behavior, we're going to be having a control plane. And just like that, we have learned what service mesh is. Service mesh does not reinvent network connectivity. Service mesh, it's a better way of doing something that we have been doing for a long time in a very inefficient way in our organizations. To recap, let's take a step back. So we have systems making requests to other systems over the network, a monolith talking to a database, or a microservice talking to another microservice. Every time we go over the network, well, the network is not secure. We have to make it secure. The network is not reliable. The network is not loggable. It's not traceable. We have to implement all those common network functionality. So we might think, okay, fine, we're going to make network requests. Then we're going to let the teams do that in their apps. Except if the teams are doing that, the application teams, they're going to be reinventing over and over again the network connectivity across different languages, across different products. And there's going to be fragmentation in how we manage the network. And because the network becomes more important, the more distributed and decoupled our software becomes, well, we need to find a better way to manage the network. So we're going to be outsourcing that network management to an out-of-process proxy binary that we can deploy alongside our applications. And in order to configure these proxies, we're going to be using another service, a control plane, whose only job is collecting that configuration and then pushing it to the proxies. This is what service mesh is. Service mesh is the combination of data planes and a control plane to be able to manage our network connectivity. No more, no less. So if we zoom out, we can see how it looks like with many services. We can see that we're going to be, and the service really can be something we build or something we deploy. A service is anything that listens on a network. And so, if we have many services, the control plane initiates connection with the proxy binaries, and it propagates that configuration. This can work across any architecture. It doesn't matter if the service runs on a virtual machine, runs on a pod, or runs on Kubernetes. It doesn't really matter. As long as we have a proxy binary running somewhere, then we need a control plane to manage that configuration. It can be on any architecture. Sometimes I hear people talking about service mesh in the context of Kubernetes and microservices, but this can be deployed anywhere. This can be deployed in a monolith talking to a database. This can be deployed on a virtual machine. This could be deployed on bare metal. From a pattern standpoint, this is a platform agnostic pattern. Service mesh is platform agnostic. Of course, the more services we have, the more microservice oriented we become, and the more network we're going to have, and the bigger the problem becomes, right? And so the bigger the requirement of something like service mesh becomes, but the pattern itself can deliver value on a monolithic app talking to a database, as well as on a microservice talking to another microservice. And of course, so this picture is actually missing a connection of the control plane to the left, but basically this pattern can be applied for both east-west and north-south traffic. So the proxy binaries can manage the network requests regardless if they are happening within the same data center or across different data centers, north-south traffic. So there are different implementations that we can use for service mesh. Of course, Kong has released one that's very specific. We've been looking, Kong as a company, as you are familiar with, we are the makers of the open source Kong Gateway, which is built on top of OpenResty and Nginx. And as an extension to what Kong does, managing APIs as a product, as an extension to that, our users were asking us how we could manage our network connectivity. So how could we make the network connectivity more reliable even before we decide to take some of that connectivity and then offering it as a product to third-party developers or mobile apps or other teams, which is more of the traditional API gateway use case. And so we looked at different implementations of service mesh that we could leverage in the open source ecosystem. And we ended up finding out that most of them are very specific to Kubernetes. And we all know that Kubernetes is a journey. So I strongly believe that Kubernetes is the future of infrastructure. But if we look at all the workloads that we have running today in the largest enterprise organizations, most of those workloads that are not on Kubernetes yet. They have to be transitioned over time, but it's a journey. So how can we make that transition, number one, faster, and also how we can deliver value on the existing applications without making that value contingent to a transition to transitioning to Kubernetes. And so, we needed something that was platform agnostic. We needed something that was simpler to use and to deploy. Service mesh, some implementations are quite complex. There's lots of moving parts. We wanted something that was simple as Kong Gateway for the API management. We wanted something simple like that, but for service mesh. And so we decided to build our service mesh control plane, which is called Kuma. And Kuma operates and bundles with Envoy as the data plane proxy. So you can check it out on kuma.io, and Kevin will show you a live demo now of Kuma. But basically, Kuma is built on top of the Envoy proxy data plane, but you don't need to have any prior expertise with Envoy. And this was another thing that other service meshes were bringing up to the table, you had to learn Envoy first, then you had to learn the service mesh, and that was too complex. So with Kuma, you can abstract away the Envoy complexity. Kuma does it for you. But of course, if you do want to go deep down and change the Envoy configurations, Kuma still allows you to do that. But you don't need to do that if you want to get up and running with a service mesh. So what Kuma does, Kuma is a platform agnostic service mesh. It can run on Kubernetes, but it can also run on top of any other workload. And this is really one of the innovations of Kuma. It supports what we call universal mode. So you can run it on Kubernetes, you can run it on virtual machines, you can run it on bare metal. It's simple to use. It bundles Envoy. You don't need to know about Envoy. So for example, if you are an Envoy user, you know that Envoy requires a bootstrap configurations to get up and running. Well, Kuma already deals with all of that, so we don't have to worry about it. And then Kuma delivers features like mutual TLS, observability, tracing, logging, and so on top of your application. And your application can be a monolith talking to a database, can be microservices, can be virtual machines, can be Kubernetes. It's platform agnostic. Kuma is an L4 product, so it manages all of your traffic, not just your traditional HTTP or gRPC traffic, all the traffic. So you can use Kuma to manage all the TCP traffic, microservices, databases, and so on and so forth, even things you download and you have not built by yourself. That communication still needs to be secure and observed, even if you're talking to Mongo or to Redis, for example. And then on top of that, it implements a series of use cases. So for example, some of the use cases it implements are traffic reliability, our security, compliance, observability, and so on. Because Kuma is platform agnostic, you can manage the system in two ways. You can manage the system with Kubernetes CRDs, so it's Kubernetes native, or you can manage it with a RESTful API, very similar to how Kong works, if you're running on systems that are not based on Kubernetes. So the teams who are deploying Kuma on virtual machines that have no expertise on Kubernetes, they don't need to know Kubernetes to use Kuma and make their network more reliable. And if you do use Kubernetes, then we support a Kubernetes native way to configure the entire system. So Kevin, in a minute, will pull up the terminal and show you the demo. But for example, these are just a few examples of, for example, enabling mutual TLS. If you want to enable mutual TLS, obviously Kuma supports Kubernetes and non-Kubernetes environments. It's very simple. You create this YAML configuration, you say mutual TLS, it's enabled, and boom, that's it. Kuma already implements built-in a certificate authority that will issue a certificate to every proxy and every workload in your system without you having to worry about doing that. You can also use a third-party certificate authority if you want to do so, but it's not required. Also, Kuma, one thing I forgot to mention, it's multi-tenant, which means that if you want to start a mesh for different teams or different products at different times, or you want to keep them separate, you don't have to start a new cluster of Kuma every time you want to create a new mesh, like you would normally do with other service mesh implementations. Kuma is multi-tenant, which means that you can start as many service meshes as you want. Each one will have its own virtual CA that's separate from another mesh, and you can support the entire organization with one cluster of Kuma. That makes the operational complexity of running and scaling a service mesh much lower when using Kuma, because we don't have to replicate a Kuma cluster for every mesh. It's multi-tenant. Another example, it's routing. So this is something that Kevin will demonstrate. But for example, if you want to route requests from a backend service to a Redis service, right? And we want 9 out of 10 requests to go to version 1.0 and 1 out of 10 requests to go to version 2.0, with Kuma, we can easily implement that by applying this configuration you're looking in front of you for both Kubernetes and virtual machines. Now, the nice thing about Kuma is that you can tag every workload with as much metadata as you want. That means you can also implement cross data center routing or failover with the same simplicity. There's policies out of the box for pretty much everything. Kong Gateway has plugins. Kuma has policies for mutual TLS, for traffic permissions, for all sorts of things. We integrate with Prometheus, with Grafana. You can integrate with Open Tracing. You can send the logs to Splunk, to Logstash. It's quite comprehensive, and we're creating more and more features every day. Plus, of course, if you want to use Envoy directly, well, even if you want to use just Envoy, you still have to build a control plane to manage those Envoy proxies. Well, Kuma allows you to apply the low-level proxy configuration for envoys by using the proxy template policy. Quite simple. And by the way, it also integrates with Kong Ingress. So the difference between an API gateway and a service mesh is very simple. Service mesh creates an overlay on top of every service that makes a request to another service. It makes that network connectivity secure, reliable, observable. Then there is going to be a subset of that network connectivity that we want to expose as a product to another team, to another mobile developer, to a developer community, and that is the API management lifecycle. So when we want to offer an API as a product, and we need a full lifecycle to manage that, there would be an API management use case. But if you want to make the network requests more reliable, well, that is a service mesh use case. So they're complementary use cases. You can start with service mesh first or API management first. It's really up to you to determine which is the best path to move forward. Kuma is open source. You can download from GitHub. There is a Slack chat and a community. So we are going to be releasing a new version of Kuma later this week. The momentum is quite fast. And we do also have enterprise usage running in production. So I spoke for too long already. I'm gonna leave the Zoom to Kevin that will demonstrate a few features of Kuma. Kevin, all right. It's all yours.
Thank you, Marco. And let me grab the screen share real quick. There we go. And I want to start off where Marco left off, right at the Kuma repository. So Kuma is open source, and we try to document everything so it's easily accessible via this repository. So everything I go through today regarding the demo application and how-to guides can be found via here. So if you were to access the Kuma repository and go to examples, here I'll give you a very short introduction that I'm going to go over and the necessary files for you to get started. So Kuma demo application is a microservice-driven marketplace, which we built to illustrate how Kuma can work in a real-world deployment. We created an application with 4 services. So as you see in the diagram here, we have a front-end service talking to back-end API and then communicating with 2 databases. And you can deploy it either in both Kubernetes or virtual VM environments. So for this guide, I'm going to go through Kubernetes, but definitely check out how you would deploy it in Universal. I think that makes Kuma very special in how easy you can deploy it in Universal, and we built out a very full-fledged guide here as well. I'm going to go ahead and go to the Kubernetes mode. It should bring you to the Kuma demo repository, which is specifically housing the demo application's code. So this is where you would find majority of the source code for the demo application. I already have Kuma up and running, so I'm going to kind of skip through the setup environment, and I'm going to dive right into how quickly you can apply these policies that add that capability on top of your application. Here, so if we go down, I'll go through how to set it up, and if we go to step number 14, you'll see that enable mutual TLS is exactly what Marco showed you earlier. All you have to do is basically use kubectl and apply this mesh policy with mutual TLS enabled. Before I apply this, let's go ahead and look at our sample application. It's running on localhost 8080, and it's a very simple graphical kind of marketplace where you can look at clothing items. You can query them. If you were to query items, this is searching off the Elasticsearch for all the items. And for each item that you look up, you can also look up reviews. And this is the reviews are all stored in Elasticsearch. So they're basically essentially the backend APIs communicating with 2 different services. But we have an issue where the communication between the services are not secure by default. The application team may not implement that on the application level. So for the infrastructure team, they can go ahead and enable that using Kuma without having to pester each application team to implement their own kind of security. And to do so, it's as simple as enabling mutual TLS and having kind of Kuma assign that certificate to each, both each services. So the communication between services are secure. So if we were to go back to the command line right now, we can take a look at our existing Kuma policy by doing kumactl get mesh. Oh, meshes, there we go. And you'll see that for a current mesh, we have mutual TLS turned off. And that's kind of the default state of Kuma when you deploy it at first. So to increase that security in our application, we go ahead, we do apply to and assign the enable true. And you'll see that now the mesh, default mesh is configured. And if we were now to go back into our application, the application stops working. And at first you might be shocked. You're like, oh no, like, why isn't it working? Like, this is supposed to automatically increase your security. And it's because that is the default behavior, right? After you enable mutual TLS, the services no longer have permission to communicate with each other. And this is where the second kind of the 1-2 punch of mutual TLS and traffic permission comes in, right? With mutual TLS enabled, you have to add the traffic permissions that tell the services who they can communicate with. So if we look at the traffic permission policy right here on step number 18, you'll see that it goes ahead and defines a spec. A spec is where you would list your source service and destination service. Essentially, you're saying, okay, for this service A, I want to allow it to communicate or send traffic to service B, right? The destination and source and the destination. Here we're going to say for all services, right? By indicating using a star, I wanted to have the capability to send traffic to all destinations. Here again. By doing so, the application all services within the application should have the ability to talk to each other. So we're going to go ahead and apply that to our mesh. We'll see that traffic permission, everything is created. And now we go back to our application. The application looks exactly like before we applied mutual TLS, where everything is working. We can still query the items for cardigan, if I spelled that correctly, and we can still read the reviews. So all 4 microservices have permission to talk to each other, and the communication between all the services are secure and encrypted. So just by using with 2 policies, we can greatly increase or lower the vulnerability of our application without having to have each application team implement their own. And while you might think, okay, for 4 services, it's not that big of a hassle, but when you start thinking of enterprise use case and start scaling your application to have thousands of microservices, it's unreliable for each application team to build out their own. And this kind of Kuma abstracts that complication and makes it much easier. So we can go back, we can use kumactl again, which is the command line application tool to both interact with Kuma. You can, in virtual machine environments, you can use that to update the state of Kuma, but in Kubernetes, we want to adhere to using kubectl and Kubernetes CRD. So you can use it to just, you can only get the current state of Kuma. So we can see that we have a traffic permission, everything by default. So I'm going to skip through logging for now. We'll get back to it in a second. But let's say hypothetically our Redis service, which houses all our item reviews, is compromised, right? Maybe we're updating a version, or maybe we want to deprecate it, or maybe someone is spamming it with false reviews that make our marketplace unreliable. We can utilize the same traffic permissions we used earlier, but with more granular control. Earlier, we specified that all services can talk to each other, but we can easily tighten that control by using service both tags and their service names. So I'm going to go ahead and delete the existing traffic permissions because we don't want all services to be able to communicate to each other anymore. And I'm going to go ahead and add 2 granular traffic permissions. The first one, as you see up top here, named front end to back end, is giving the front end service the traffic permissions to talk to the back end service. So we're going to go back to the diagram of the application. Let me pull that up real quick. as you see that we want to give this application the permission to talk, this service the permission to talk to this service. And then we have to add a second traffic permission now because we need to also enable backend API to talk to Elasticsearch, right? So this is where you see on the second part of this policy, we'll have a traffic permission for backend to Elasticsearch, and we specify the source destination, a source service, and the destination service. So by adding these two traffic permissions and leaving out any kind of traffic permissions that specify the Redis service, the expected behavior would be the application would work as how we saw earlier. We can query the items, but if we were to click on each individual read reviews, the reviews should not load because essentially this backend API that's powering the marketplace will no longer communicate to any of the Redis endpoints. So we can try that. Let's just refresh for good measures. So clearly our Elasticsearch still works. We still have permission to communicate with that. We can still query for leather jackets. But if we were to look at a review for the cardigan, now the review no longer loads. And that's because now the backend API no longer has that permission, right, to communicate with the Redis service. And this is how quickly you can start kind of adding that granular security policies to your application within your organization without having each team to make changes. So just as easily we can revoke Redis's permission. Let's go ahead and re-enable that by adding our last traffic permission, which is back into Redis. And now our application will go back to its default state where the user can now look at reviews. And as we go through this, you'll see that kind of ongoing theme where we try to make it as simple as possible to get up and running by making these policies easy to apply, right? And for folks that are unfamiliar with how would I go ahead and get these kind of find the service name or the destination name. In Kubernetes, it uses kind of Kubernetes like name conventions, right? Like the service name and the namespace that it's being the service is in, and the service and the port. But in virtual machine, you can easily just specify the service name, and that will work. Okay, so we talked about mutual TLS. We talked about how traffic permission works alongside mutual TLS. Let's go ahead and look at traffic routing. Traffic routing is powerful because you can do stuff like canary deployments or blue-green deployment. And to illustrate that, we're gonna need a few more versions of our backend application. So here I'm gonna deploy scale up additional replica of our V1 backend. So we have currently, and the V2 and a V2 of our backend too. As of right now, sorry, I don't have a diagram for that, but to kind of walk you through what's happening is that our current application, if we look at our pods, we have the V0 was our existing backend service, did not support any sales. So let's say holiday season is coming around and you want to enable sales in your marketplace. You want to kind of roll out new versions of your backends to support new features that might be critical during those kind of the holidays. So to test out kind of the sale capability of Kuma Marketplace, we're going to roll out V1, which is it supports one sale that will basically place one item on sale for 50%, and V2 will place 2 items on sale. But if we were to deploy it like that, we scaled up our deployment, you'll see that suddenly one out of every 3 requests will go to one of those backend services, right? It's just, and we don't have that control over, what traffic, like what percentage of traffic goes where. And this is where we can use traffic routing to, we already have traffic permissions that enable front end to talk to backend, but now we can use traffic routing to say, okay, which specific backend service I want you to talk to and how I want you to communicate with that. So you'll see we have our front end talking to 3 backends now, and we're going to use traffic routing policies to limit, how many users see our new service. So we can kind of do a canary deployment and not break our kind of production environment. So if we look at the traffic routing policy over here, the metadata will look very familiar where you can specify name and the namespace of where it is. And then in our spec, here we have the source and destination service. Once again, if just like earlier how we specified source and destination in traffic permissions, you would specify here in traffic routing as well. The difference with traffic routing is there's additional configuration section, as you see here on the lower section, where you could apply a weight to the different destination services. So here for our first configuration, we're going to apply a positive weight of 80 to destination service with a version tag of v0. And this version tag goes back to what Marco talked about earlier, where you can apply as many tags as you want to each service to give you granular, like kind of, so you can be very specific of how you want to route your traffic in the future, utilizing these tags. So we're going to use a version tag. You can add other tags like environment to label your production, or you could also add your zones to see which zone your service is deployed in. This is all up to you and how you want to deploy Kuma alongside your application. So for us, since we're just doing kind of canary deployment example, we're going to send positive weight of 80 to our backend service of v0. This is our existing code. And we're only going to send a weight of 20 to our v1 version, which is our new backend service that enables one sale. Meanwhile, we also have our v2 version, right? Let's say v2 is just, there's too many new changes. Maybe the intern worked on it, so we want to make sure it doesn't hit production just yet. So we're going to apply a weight of 0, which means we'll send no traffic there. Let's go ahead and apply this. So we create our traffic permission front end to back end. And now, before I refresh, you see this is the v2 version, right? There's 2 sales, and we want to make sure we don't get this. If I start refreshing now, the expected behavior is that you'll no longer see that v2 application. And only maybe 2 out of every 10 requests, you will see that sale come up with one sale, right? So I've refreshed it 5 times now, 6 times, 7 times, 8 times, perfect, right? The sale pops up, and this shows that the traffic routing is indeed working as we specified. Over time, if you get more confidence in your v1 application, you can go ahead and scale the weight maybe up to like 50-50, and during holiday seasons you can make it like 100, like you can scale v0 back to 0 and only apply a weight to your v1 version. Awesome. So let's take a look at time. We're already at 2 o'clock. Marco, is there anything else you want to illustrate? I'm going to go over the GUI next. I think that's all we have time for now. Okay, if there's no opinion. So far, everything I've shown you so far is done via the command line. So using kumactl, right? So you can do kumactl get meshes, kumactl get, and you can see all the different kind of policies you can look up. But in order to make Kuma the experience with Kuma easier for the user, we actually built out a GUI. So as you can see here, this GUI, the Kuma GUI, gives you a very easy place to understand what's happening in your mesh. So for our mesh our default mesh, you can see that we have 6 data planes. We can go ahead and inspect those, and those 6 data planes would correlate with the different services we have in our application. So here you'll see the v1 and v2 backend, all the different tags that you have applied to it. This is also where you can get the service name right here, like the backend.kumademo.svc. And it's a very easy, simple, and user-friendly place to kind of check if any of your policies have been applied. So if we go to like our traffic permission policies on the left here, you'll also see the 3 traffic permission policies that we have in place. Aside from that, there are a lot more policies that I'm not going over today. I'd say definitely check out the Kuma, the IO website. And as we add more and more releases and more functionality. I'm going to continue to update this Kuma demo repository with guides of how to utilize those policies alongside an application. So thank you for tuning in. If you have any questions regarding Kuma demo, if you're running it, you have questions, this is also an open source repository, so you can go ahead, open up an issue, open up a PR if you think you can help with the community and add a fix. And I think that's it on my side. I'm gonna hand it back to you, Caitlin.
Hey, Kevin. Actually, yep. I'm going to wrap it up real quick.
Perfect.
So if you could stop sharing.
Yep, all yours.
All right. So can you see my screen?
Yep, looking at it now.
Yeah. So basically, just to wrap it up, we took a look at what were the transformations in the industry from a technology standpoint that shifted the way we build software. And the more distributed, the more decoupled we become, the bigger connectivity, the bigger role connectivity takes in these new modern architectures. Because decoupled, distributed means that we're going to be relying more and more on network requests from one service to another, from one data center to another, from one cloud to another, in order to operate these new modern architectures. The network, it's unreliable, not secure, untraceable by default. It can be very problematic. And so we need to make it more secure. We don't want the teams to be building this from scratch, but we want to provide the teams, the application teams, with a solution that allows them to just forget about the network because something else is going to be taking care of that. And that is the service mesh pattern in a nutshell. So we're going to be providing a data plane proxy that runs alongside every service. And then we're going to be providing a control plane like Kuma that's going to be managing all of these proxies. We're going to be leaving the chat open in Zoom if you have any questions. But in the meanwhile, if you you can give it a try. You can see the things that Kevin has described on Kuma.io. You can install it, download it. It's open source. Let us know your feedback. So thank you so much.